Good morning, linear algebra. How are you? I am actually out today for a family funeral. The good news is that this is actually not an emotionally traumatizing funeral. It's something that has been kind of long expected for someone who lived a very, very long and full life. So it's actually, in my opinion, kind of a happy occasion. It's like a celebration of life, so to speak. But what that means is I am not there with you for the lesson for today. So hello, Miss Screen. What I'd like you to do is just listen to this screencast here, and this will kind of take the place of the digital lesson. So maybe you'll take a few minutes to talk about your polynomial interpolation homework first, those two questions that I gave you for homework. Just why don't you take a few minutes to talk those through. Oh, the other thing is the 10 minutes you need for question number 2 in the test. I will take care of that when I see you next, okay? That will certainly be addressed. So here's the lesson for today. First of all, go over the polynomial interpolation question, okay, together as a class. Make sure there are just no stones left unturned. If there are someone in the class, please just make note of that. And then when I see you next, I will address those questions. So once you do that, then proceed with this screencast. So this lesson here is today is we're moving on to kind of the second chapter of our text, which really kind of goes into, in a much more detail, the determinant of a square matrix. Something we've done just cursorily, certainly cursorily in in multivariable when we needed it. But this second chapter of linear algebra really is about the determinant as a function, and the determinant as something, a number that really allows you to determine certain properties of the matrix. And then, of course, there are all these incredibly cool things that happen when you find determinants of certain matrices, which are just really wild. It's really kind of fun. So, but before we go into the new stuff, let's just do two brief recalls. Recall that with a 2x2 matrix, if A is a 2x2 matrix, you recall that the determinant of a 2x2 is just AD minus BC, right? Okay. And we also know that if the determinant of A ever equals 0, the inverse of A does not exist. Okay, so you remember that we talked about, I know. Another way, just before I move on here, see how I wrote determinant of A? You can also see determinant of A or determinant of a matrix written this way, the straight bars, the determinant of A, B, C, D, right? So these straight bars here mean determinant of. Okay, recall number 2 might be a little bit distant. We did this last year in multi when we needed to find a cross product of two vectors. If A is 3x3, the determinant of that 3x3 matrix is, you remember this, everyone? We kind of, I think I called it, we ran across row 1, right? And we ran across row 1, and I told you, if you run across row 1, make sure you just make a note, it goes plus, minus, plus, right? And when we run across row 1, the determinant of that matrix A is, right, it's positive A, and then what you do is you cross out the row and column that A are in. It's positive A times the determinant of the remaining 2x2, right? And then it's minus whatever the entry of B is, so hence the minus, and then you kind of mentally again, and forgive me with the colors over covers, so it's minus the B entry, you cross out the row and column it is in, and you'll have this 2x2 remaining, so minus B times the determinant of the remaining 2x2, and then plus the C entry times the determinant of the remaining 2x2, okay? That's how we found the determinant of a 3x3, and we ran across just row 1. And I remember, I think in one or both of the classes, someone said, like, can we run across any row? And I said, yes, we can, and we'll talk about that in much more detail in linear algebra. Okay, in fact, we're going to talk about it today. So that's how we found a determinant of a 3x3. We ran across row 1, and we kind of took each entry in row 1 times the determinant of the remaining 2x2. We add all these up. And as with the case above, if the determinant of A equals 0, the inverse of A does not exist. And actually, everyone, that's universally true for any square matrix. If the determinant of that matrix equals 0, that matrix is not invertible. Okay, and so I just wrote here, so the determinant of an n by n allows you to determine certain things about the matrix. And one of the things you can determine is whether or not the matrix is invertible. So what I want to show you right now, so new topic number 1 here is how to find the determinant of an A using an advantageous, it's called an advantageous cofactor expansion, okay? That is just the mathematical way of saying how to find the determinant of A by running across an advantageous row or column. So now what we're going to do is allow for the possibility of running across not just row 1, but an advantageous row. You can also run down a column. So that's how we use an advantageous cofactor expansion, okay? Before I show you that method, one thing I want you just to make note is the following. We started with saying that row 1, if you run across row 1, you have to remember it goes plus, minus, plus, and I'm going to put a dot, dot, dot here because it could be more than a 3 by 3. But the point is that, row 1, you always run across plus, minus, plus, dot, 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 okay? Once you know row 1, which you do, the great thing is that the other rows and columns have to fall into place. So it goes plus, minus, plus, then it goes, okay, watch, then it goes minus, plus, minus, dot, 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 plus, minus, plus, dot, 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 minus, plus, minus, dot, 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 okay? And I'll put dot, dot, dot in both directions here. So the point is that you see a pattern, okay? So once you observe this pattern, what becomes really advantageous is if you're asked to find this. Let's say you're asked to find the determinant of 2, 0, 1, 0, 3, 8, 7, 0, 14. Okay. And I'm asking you which row or column do you want to run through advantageously. And when we say advantageously, we mean just in terms of minimizing the busy work and minimizing the time. I'm going to choose to run down column 2. Okay, because of the zeros. And when you run down column 2, let me show you what happens. This is going to equal, well, it goes, remember, it's minus, plus, minus for down column 2. So it becomes 0 times the remaining 2 by 2. Let's just write it out so we know what it is. You're going to cross out the row and the column, the 0 in, times this determinant. Okay, and then you're going to plus, the entry is 3 times the remaining determinant here, which is 2, 1, 7, 14. Then minus 0 times the remaining determinant when you cross out and cross out, 2, 1, 0, 8. But the reason why we chose to run down column 2 is because the 0, right, that's what happens there. And at the end of the day, the determinant is just going to be 3 times the determinant of the 2 by 2, which is going to equal 3 times 28 minus 7, which equals 21 times 3, which equals, what is that, 63? Yeah, 63. That's the determinant, okay? So very quickly here, the determinant of a square matrix, you can run down any row or column, but the row or column you want to run down is the one that has the most zeros, okay? That's how you use an advantageous, it's called a cofactor expansion. All right, now here's what I want you to talk about. Can you all derive for me, let's say, let A equal an upper or triangular matrix. Doesn't matter, okay? It doesn't matter. Pick one, upper or triangular. can you derive what the shortcut is for the determinant of A? Okay, A is an upper or lower, whoops, I meant to put upper slash lower. What did I do there? Upper slash lower triangular matrix. Can you derive the particular interesting fact about the determinant of an upper or lower triangular matrix? Go ahead and discuss together and see if you can derive it, then replay me. Okay, here's the proof. So if I just did here a lower triangular matrix, and I said let A, look at the red with me here, let A equal this lower triangular matrix, and of course the dot 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 just means that this pattern here could go on forever as long as the matrix is square. Of course, that's kind of redundant to say because an upper or lower triangular matrix is always square. But for the purpose of this proof, I just chose the 3 by 3 here in green, okay? I'm going to choose to run down column 3 as an advantageous cofactor expansion, and look what happens. If I run down column 3, and column 3 here is going to be plus minus plus, that's how it's going to go, the determinant of A is going to be F times the determinant of the remaining 2 by 2. And when I flush that out, look what happens. It's going to be F times the quantity AC minus 0, which equals just ACF, which is merely a product of the diagonal entries, which is a pretty neat thing. And that's what I mean about just kind of these cool mathematical properties of the determinant of square matrices. So one thing that you've just derived is that the determinant of whether it's an upper or lower triangular matrix is always equal to the product of the diagonal entries. Okay, here's the last thing I would like you to work on here to kind of close out your discussion day. Interesting question. Another example here, we're just beginning this, but still there are some interesting questions that you can do. This will be a nice discussion point. Look at this equation that involves determinant, okay? What I would like you to do is to work together to prove that or show that the determinant of this matrix here, again, where X and Y stand in for variables, and A1, B1, A2, B2 are the ordered pairs of just 2 points on the two-dimensional coordinate plane. And these are just ones, obviously. That the determinant of this matrix, if you set it equal to 0, this equation here describes the equation of the line through these 2 points. Okay? All right, so that is it for class. I'd like you to do this in class, though. Don't just get up and just say, oh, the screencast is over. We are going to run out of here. No, this is a discussion point right now. Okay? And I will post homework on the teacher page later on today. All right, bye, everyone.